I am myself a computational mathematician, and Richard Tapia is somebody I've known since the very beginning of my career and the highest admiration for him, so it's a very exciting moment for me. Richard Tapia's life story is sort of the classic American immigrant story, at least in the beginning. His parents left their home country at a remarkably young age, typically, in their case that country was Mexico, in order to seek a better life here in the United States. They met in the U.S., where Richard was born, and he was raised in southern Los Angeles in the barrio. And he's the first member of his family to attend college. I suspect his parents were extremely proud when he left his job with his welding mufflers and enrolled in Harvard Community College and got a 2-year degree there. But that's where the story stops being the standard archetypal story, because it wasn't another few generations before he rose to the top. Rather, his talent and drive were extraordinary. And he went on to UCLA immediately. He got a bachelor's, a master's, a 1967 PhD degree from UCLA. Not only a PhD, but a PhD in mathematics. And now, 35 years later, it took you a while, but 35 years later, he's among the best-known computational mathematicians in the world. He's a leader in the field of optimization, which is the field that our institute dedicated last year to. The first couple of years after his PhD were formational years for Professor Tapia, and I'd like to say a little bit about them. He spent those years as a postdoc at the Mathematics Research Center, which then existed at the University of Wisconsin in Madison. In those days, the MRC was widely known as the center for applied mathematics in the country. And Richard has described to me at length how important the existence of the MRC and his chance to be there at the beginning of his career was to him. The people he met there, the ideas he encountered there, the collaborations that began there, set the direction for his entire research career, and they continue to ramify to the current day. The reason I'm emphasizing this point is because while the MRC sadly lost their funding, I think in 1987, and has disappeared from the face of the earth, most people in the mathematical sciences world would agree that a similar role has been filled for the last 2 decades by the Institute for Mathematics and its Applications. We have our IMA postdoc program that jump-started the careers of many days in the mad scientists and continue to do so. Many of our IMA postdocs are in the audience today. I really want to emphasize this because not all Minnesotans, maybe not even all IT alumni, are aware that the most important center in interdisciplinary mathematics is sitting here, right here in Minnesota, and making a tremendous impact. Okay, sorry for the digression, but Richard himself is famous for digression, so I'll explain. After leaving the MRC, Tapia joined the faculty at Rice University, and he rose through the ranks very quickly. In 1991, he became appointed the Noah Harding Professor of Computational and Applied Mathematics. He served Rice in manifold capacities. You couldn't imagine a better citizen for his university, and wisely. He was the chairman of the Department of Mathematical Sciences for 5 years. Since 1999, he's been the director of the Center for Excellence in Equity in Education. On top of his extensive and well-known research in computational math, for which, for example, he was inducted into the National Academy of Engineering in 1992, he's been an unbelievable teacher and mentor in mathematics. He graduated nearly 40 PhDs, and through his unflagging and incredibly effective efforts, he's made the Rice Computational Applied Math Department the national leader in the production of doctorates in the math sciences from underrepresented groups. And Richard takes a very wide view of underrepresented groups. He's interested in all underrepresented groups. He's been widely honored, as you might expect. It would be unwise for me to try to list even all the significant honors. I've already mentioned he's a member of the National Academy of Engineering. By the way, he's the first native-born Hispanic member with that honor. In 1996, he was appointed by President Clinton to the National Science Board, and he received the Presidential Award for Excellence in Science, Mathematics, and Engineering Mentoring. Next year, he received the Lifetime Mentor Award from the American Association for the Advancement of Science. In 2000, he received the Distinguished Scientist Award from the Society for the Advancement of Chicanos and Native Americans in Science. And in 2001, the Reginald H. Jones Distinguished Service Award from the National Action Council on Minority Engineers. Just last month in Atlanta, the ACM, Association for Computing Machinery, and the IEEE Computer Society hosted the second biannual Richard Tapia Celebration of Diversity in Computing. Even in this abbreviated biography, you have to believe me, I abbreviated it a lot, you can see the incredible graphic contributions of Richard Tapia. Here's a person who's not only remarkable achievements, but also receives a remarkable balance in confronting many challenges and many responsibilities of being a scientist and an educator and a citizen in a complex, technological, multifaceted, multicultural modern world. Also, he owns two of the nicest damn 57 Chevys that you'll ever lay on. So it's truly a great pleasure and honor to introduce Professor Richard Tapia to speak on math and top speed.
Thank you. Thank you, Doug. Okay. Thank you. It's a pleasure to be here. And we'll go into this talk, but let me tell you how the talk started. A few years back, I was at a meeting. It was a math meeting at Stanford, and a very distinguished mathematician spoke on the mathematics of exercise. And a lot of the things he said, I said, we know that from cars. And I was sitting next to a colleague of mine, and I said, I could give a talk on cars like this. And he said, do it. So it happened that this was the SIAM, Society for Industrial Applied Mathematics. And the president was sitting over there. And I went up to the president, I said, invite me to give a talk for next year, so I have to prepare it. And he said, okay, you're invited. Okay, so now I have to prepare it. But that's the deadline I needed. But I am going to share with you a lot of my life. This is really not, this is my therapy. I've had a need for therapy in a lot of ways. So I'm trying to show you that I'm going to combine things that have to do with mathematics, and you'll see how I grew up. So to me, this is therapy. This is what I do when I'm all stressed out on other areas, is I try to put together talks on issues like that. And this one is on drag racing. I have one on bicycle racing, one on gear ratios, one on other stuff. And one of the things that I do is address this. The main purpose one of the purposes that we do is I do want to show the youth of America that mathematicians don't have to be boring, dull all the time, okay? That there's a lot of things that we can do that are really fun, and that math in itself can be fun. So you notice that one of the undergraduate students I have at Rice drew this car. So I mean, he free-handed, his name is Joseph Cifuentes, and we added this at the bottom. And we're gonna add sound to it, but we haven't had time to do that yet. But I have some beautiful sound. Now you can notice it comes in, and look, it shakes. See, it's idling. See, it's shaking. See, and then it takes off. And when it goes, Joseph had it going off at a constant speed. And I said, there's no acceleration. So in terms of frames per second, it's accelerating at 2. Okay, it doubles every time. Every time unit, it doubles. So Joseph did that. So we're going to talk about math at top speed, and we're going to basically go through quick. Now, there's a lot of people that I have to acknowledge, but we don't have time for that right now, okay? So, look, car club members, family, Rice students, assistants, colleagues, Carl DeBoer and I have had many discussions, Paul Spanos, who is one of the world experts in mechanics, and we argue, I get to argue a lot with a lot of people, okay? And the support for this. Now, let's start with this picture. This is a picture which in 1995 ended up on the cover of SACNA's News. And SACNA's is the Society for Advancement of Chicanos and Native Americans in Science. And what was happening is they wanted something that would relate to the youth. So they said, let's take a mathematician, let's take somebody who basically they could relate to, the Mexican American, and let's take a car and put it, and that's the picture that ended up on the cover. Now, it went many places, and I share with you one of the funniest things is that Neil Lane, my colleague, was presidential advisor, or science advisor to Clinton. And so it got to the White House, okay? And Neil Lane calls me and he says, Richard, this picture has come, this great magazine. And he said, but I'm trying to find the centerfold and I can't find it, okay? Okay. And I said, Neil, you'd be very disappointed if you found it, okay? So this is a standard introduction here. It said, so what am I thinking, okay? Has mathematics improved the quality of my life? Or has it just made me dull and one-dimensional, okay? And I say no. My mathematical training enters into everything that I do, and has definitely made my life more enjoyable and more interesting. It's allowed me to combine 3 of my loves. Notice I say family, cars, and math, okay? And it has in many ways. So in this talk, I hope to demonstrate this to you. Now here's drag racing. The greatest show on wheels. Motorsports are this country's most popular sports, okay? I mean, motorsports collectively, more than basketball, you know, baseball, football stuff. And within motorsports, drag racing is the most popular. And even though a lot of people haven't seen much about drag racing, it is a very, very popular, well-attended sport. I parallel two things, drag racing and rock and roll. Both born in America in the 50s, went crazy in the 60s, had similar origins and patterns. Now, the part one of the talk is going to be background and introduction. So I'm going to tell you and I'm going to show you about drag racing. Then part two will be mathematical stuff. And so in some of the part two, there's some technical things. But enjoy the first part, know where you're going, and then we'll gloss through some of the math as we have, but you'll understand what I'm trying to say in this thing, even for those of you who aren't mathematicians. So I'd like to start this out with something that I really mean. Drag racing is the only major sport I know of where women have competed successfully with men. And there's legendary Shirley Cha-Cha Muldowney, basically three-time world champion, 1977, 1980, 1982. Laurie Johns and Shelley Anderson. And we'll a little bit more on this. So there's Shirley. So watch this race. I don't know if you can see it, but on the inside is Kenny Bernstein, and Shirley's on the outside. And Shirley wins the race. This is her pit crew. That's Shirley with the 2 parachutes to stop, and that's Shirley being interviewed saying, of course, it was a hard race, and I'm glad I won, and he's such a great competitor, okay? Now, this is Laurie Johns. Laurie Johns is out of Corpus Christi, Texas. Very popular, autographs all the time. And watch, Laurie's on the outside. There's Dick LaHaye. This is the bachelor. That's Laurie's mother, okay? Now watch. So Dick LaHaye, this is the Nationals at Pomona. And Laurie's again saying, I don't know how I won, but I guess I did, okay? Very popular, very popular. So basically, that is, that's okay. I think we can turn those down. So here's some terminology. I like the lights down a bit. Okay, here's a, we don't want people to fall asleep, okay? Okay. Here's some terminology. Look, we're going to lose top speed, or miles per hour. It's the velocity in miles per hour that a dragster has reached at the end of the quarter mile. Top speed. So that means you start off in the quarter mile, how fast are you going when you get to the end? On the other hand, elapsed time means how long did it take for you to get there? They're different things. How long did it take to get there? How fast are you going when you get there? Fast describes a good top speed. Quick describes a good elapsed time. And we're going to get into issues about quick versus fast. Okay? So the birth of drag racing, early 50s. Now the birth of any era is characterized by many wonderful, beautiful things. Experimentation, innovation, ingenuity, creativity, boldness, large variances, informality, and fun. And basically drag racing was certainly that. So we go back and say, analogous situations for mathematics, for science, for disciplines, for music. Okay? Basically at the birth of an era, there's a lot of variance, a lot of fun. So I would like to use drag racing as a metaphor for this variances. So let's talk about the first dragsters. We're going to go through fast on some of these earlier shots. Here's Dick Kraft in Santa Ana in 1950. And notice that dragsters have a nickname called rail jobs. And here's Dick Kraft exposing the rails on basically his 1933 Ford. So he just started taking things off and taking things off, okay? And the more he could take off, the faster the car would go. And so he has some hot rod equipment. Look, he has some heads on there. It's a flat head. But basically, that thing went 110. And so this is probably what coined rail job. Here's Joaquin Arnett driving the Bean Bandits car. Now notice it looks like half roadster in the direction of going towards a dragster. Now, one of the most incredibly impressive individuals I've ever known in my life was Mickey Thompson. Mickey Thompson was not formally educated, but incredibly creative. His idea was to put the driver behind the rear end. Therefore, the weight transfer would be extremely effective. Mickey not only did that, notice that he put discs on the front wheels, he also put the rear wheels close together to try to act as one wheel. So Mickey Thompson, incredibly creative, incredibly ingenious, had land speed records, and for those of you that follow the sport, about 15 years ago he was assassinated for, actually, maybe we'll talk about that, maybe we won't. But anyway, so this is Santa Ana, 1954. Here again goes what is called a slingshot. The driver sits behind the rear wheel. This is Emery Cook in the Cook and Bedwell car, which had the world's record. And Emery Cook, This is actually now a production car. This was built by Scotty Fenn. So where Mickey built his own, this was actually production car. So if the engine, the driver behind, the engine sideways, a legendary car, Jack Christman. If you put the engine sideways, you can take advantage of the torque of the engine, either to hold the front end down or to put more weight on the rear end. So it's a good idea, and let's try it, and Jack Christman did quite well. Let's think of rear engine. Here's Lyle Fisher in the Speed Sport Special in 1957 that actually set the world's record. Here is a roadster with the driver sitting in front, and see the engine is behind the driver. So we're trying about different things. Okay, what about aerodynamics? Here's Jocko out of Lakewood, California, built a car and streamlined it and tried many different things. The streamlining, we'll talk about later, was it effective or not, but it made it a little bit heavy. Aircraft engines. The legendary Green Monster out of Akron, Ohio. Art and Walt Orphans. That is an Allison V12 or V16 aircraft engine, very heavy with lots and lots of horsepower. Jet cars. Here's Roger Harris driving. This is a thrust engine. Notice that he is basically, I mean, that's a jet car in traditional sense of the thrust engine. Okay, how about two engines? Here's the Bean Bandits in 1952, where they put two Ford engines in front. So up there it says two in front. Here's one of the most, along with Mickey Thompson, one of the most ingenious people I've ever met was Lloyd Scott. He designed this, and he has two engines. He sits in the middle, and he has one engine in front, one in back. The one in front is an Oldsmobile. The one in the back is a Cadillac. He shifts the one in front. He doesn't shift the one in back. Engineering masterpiece. He set the national record and won the first nationals in 1955. Incredible. Now, Don Jensen at that time was fascinated by Lloyd Scott, and he built a car, but he decided to put two Cadillac engines behind the driver. There's two behind. Now, this is one of the most ingenious. This is Eddie Hill out of Wichita Falls, Texas, and let's go back. Okay. So let's go back in this one, okay? So here's Eddie Hill. Now notice what it says up there. The engines are actually part of the frame. See, look, he builds the frame, then he bolts it to the front of the engine, then he puts two engines, and then he essentially finishes it off. And also there's four wheels, there's four tires. So basically, you have to say, now Eddie Hill has a degree in electrical engineering from Texas A&M, okay, he's out of Texas. So very bold, very creative, and you have to say that that car, bold, creative, two Pontiac engines with superchargers, and you know the engines are part of the car. Okay, if two engines are good, then four should be better. Okay? and here's TV Tommy Ivo, who was on the Donna Reed show, was a musketeer, was a very popular figure in Southern California in the early days, and he built four-engine car. Those are four Buicks, and it went really good. And here's Tommy Ivo going down the strip with his four Buicks. So in spite of often attaining better times, both elapsed time and mile per hour, all of these designs were racing failures when compared to the single-engine slingshot. The cars were either too bulky, too inflexible, not agile, too heavy. However, the slingshot became too dangerous. The driver sitting behind the machinery would be critically hurt or killed when machinery exploded. Engines exploded, superchargers, rear ends, clutches, flywheels. In 1970, after a very serious accident, Big Daddy Don Gartless designed a car that put the driver in front of the noise and machinery, and this turned out to be today's Dragster. It's not a slingshot, but it's close to it. Now here's a shot of Gartless in Long Beach when his car. The flywheel came off, cut the car in half, the car kept going one way and Gartless went the other way. It ended up in the hospital for 6 months. And that's where he had time to say, something's wrong with these cars, are too dangerous. So here's today's cars. On TV, you've all seen the legendary Budweiser King, driven by Kenny Bernstein, and last year his son. But that's what they ended up. So that's the design that Gartless came up with. Now here's our humble beginnings, about 1957. That's me standing in front of our 1957 Chevy in 1957. This is my wife about a year later, in about 1958-59, next to the 57 Chevy. Now this Chevy ran really good. And so we took the engine out of it and built a Dragster. Okay? And we decided that we would take that engine from the Chevy. It was a 270. It had a national record. And we put it in a little home-built Dragster there. And we built it. Notice it has motorcycle wheels. And it was a little small little car with a Chevy engine. And we went racing. But we were barely out of high school. So we had no money, we had no resources, so we couldn't afford a lot of stuff. There we are working on the car. My brother sitting on the wheel is Steve. He now has a law degree from Yale and he works for Bill Gates, but that's when he was 6 years old, okay? Now, we couldn't afford a trailer, so we put it in the back of a truck and went racing. Okay? Okay. Now, we're going to get into a little bit more, but look, the essence of drag racing, quick versus fast. The driver of our cars was my twin brother, Bobby. Bobby was a very good driver. We worked together, we built cars, but Bobby was a better driver than any of our friends, okay? So Bobby became the driver. But somebody thought it would be a great idea if we had a match race in Long Beach between the little tiny Chevy, we used to call it Almost Grown, and the great big green monster. That would bring people up. So we decided to have a match race with Bobby in our little Chevy and the green monster. And of course, we won, or else I wouldn't show you this, okay? So Bobby got the title of the Giant Killer. Now, there we are. Notice here's Bobby in the little Chevy out in front, and there's the green monster getting beat, okay? And so we're going to return to this shot. But we won, and as everybody was very happy because we were the underdogs. We were basically high school kids, and here was this professional big monster, and it was sort of David and Goliath. Bobby kept driving, my brother, and in 1965 he set the Long Beach Strip record, which was probably the most famous strip in the country, in this car, which belonged to Larry Stellings. And Bobby's on this side, smoking the wheels. Bobby continued till in 1968 he set the world's record in a car, the same car owned by Larry Stellings. So it was February 13th, 1968, where we set the world record. But that's the time that I got a PhD in 68, and my brother got his undergraduate degree. And so this is about the end of our racing days. Essentially, we got to the point where we set a world record, and we said, now let's go off and conquer new frontiers. Last year, very satisfying event. My twin brother was inducted into the NHRA Hall of Fame as one of the top drivers of all time. Okay? Now, this we're going to get through. Okay, drag racing today. Let's do this. I'm going to show you a video of the world record run by Larry Dixon in Houston, Texas on April 9th, 1999. And let's see if it comes up. There it is. Okay. So there's a world record run. A lot of world records are set in Houston because many people say that we're sea level, okay, so our elevation is 0, but it's actually, I think about -5 right now, okay. So, look at this burnout. This is called a burnout. Before the race, you take the car and you run down the strip for a little while to heat the tires. So the tires get hot, gooey, and sticky. You have to have the burnout. This will come back later on, but that was a burnout. You just, before the race, every car spins the wheels really hard, so they get very hot, very gooey, and very sticky. And this is going to come back. Many dimensions of dangers, because these cars are basically running at the edge of the laws of physics. So what I'm going to show you right now, some of the scenes you're about to see show violent accidents, but in every case, the driver was not hurt and walked away. Otherwise, I wouldn't show that particular shot to you. So here we're going to go. This is Shelley Anderson, world's fastest woman. So, y'all watch this, okay? What it says?
You'll see why. We have a problem.
I want to show you that he's not hurt. So watch that he comes up, and he's clearly dazed, okay? But the safety safari comes up and picks him up and says, you know, how many fingers do I have up or whatever, okay? Okay. Now this next shot is Raymond Beadle in the Blue Max out of Dallas, Texas. Raymond likes to drive. He loses the body. He says, I'm going for the race, okay? Okay? The parachutes come up. He can't drive. The parachutes are up. So Raymond Beadle, being the showman, he says, okay, I couldn't continue, but I know the crowd loves me. I will acknowledge the crowd, and he does. And it's, okay. And it's just like a scene out of Rocky, okay? It's just like a scene out of Rocky. So there's no doubt that a lot of the things that, I mean, I skipped a slide saying that rules are imposed on dragsters, limitations in terms of weight, horsepower, gear ratios, and they're all done in terms of safety. In other words, they're done so that people, what's happened is the cars are going too fast before the technology of safety, so that you have to slow them down. And every year a new rule comes to slow them down. In spite of that, we're going to continue. So that was part one. Now we're going to part two. Part two is, okay, 4 studies about things. So mathematical study number 1. Many people have always asked, what's the true speed as opposed to the clock speed that today's dragsters achieve in a quarter mile? And considerable attention is paid to the first person who went 200, 300, or 400. 400 hasn't happened yet. Now there's 3 types of error. Okay? Truncation error, that's for mathematicians. Clock placement error, that's for the people who put down the clocks. And then clock resolution error, and that's the mechanical resolution of the clock. So let's look at all 3 of these things and see what they say. Now, what we're going to do here is we're going to continue many times to write the dragster trajectory as distance as a function of time. So S says distance as a function of time. So we're going to have a mathematical model, and we'll write oftentimes we're going to put distance as a function of time. Now, for those of you that know mathematics and physics and mechanics, the first derivative is velocity, change in distance with respect to time as velocity. And the second derivative, which is change in velocity with respect to time, is called acceleration. Okay? So we'll try not to spend too much time on that. But here is the way the speed is measured. You have 2 clocks, and you take 2 readings, and you do a difference quotient that's on the right-hand side to approximate the time. So to a mathematician, this is a first-order backward difference approximation to the derivative. To a physicist, this is simply the average speed in a time interval. And average to a physicist means the constant speed needed to perform the task. Whatever you had to do it at a constant speed. So people are intelligent, and they say if that's average speed, then here's what people have believed for years. Since clocks give average speed in the time trap, dragsters are really going faster by about 2 to 3 miles per hour at the end of the quarter mile than indicated by the clock speed. So we'll do a little bit of analysis. So here's what we're going to do. We first prove a theorem. And that says that the difference between the true velocity and the difference quotient is basically given by 1/2 the acceleration at some point times a constant, which is positive. So basically, this is standard in numerical methods that you show that the true derivative minus the difference approximation is the second derivative. Okay? So the proof is straightforward application of Taylor's theorem. We don't want to worry about that. But here's what happens. If acceleration is positive in the time trap, then dragsters indeed are going faster than they're clocked. They're clocked. And you can look at that in many ways, convex functions, whatever. But basically, if the acceleration is positive, which it is, then dragsters are going faster. So let's see how much. Remember, people believe it's 3 miles per hour. So what we do is we go back and we ask the National Hot Rod Association for data they have. And they have the dragster timed at 60 feet, at 330, at 660, at 1,000, at 1254, and 1320. So we take those 6 pieces of information, and then we know that distance at time t equals 0, it hasn't moved, is 0. And we also know that velocity, the speed at time t equals 0, is 0. So we have 8 pieces of information. So now we can play games with those 8 pieces of information. And if we do higher order interpolation, that means take basically a polynomial of degree 3 through 4 points, degree 4 through 5 points. It turns out that indeed, notice that the difference is that, yes, they're going faster. If we use a cubic, it's 0.4 mile per hour. But if we get better and better accuracy, it says 0.18. So basically, we can safely say that, yes, they're going faster, but while mathematical truncation error is in general positive, it's negligible. It's less than a half a mile an hour. It's not 3 like you thought it was. Okay? Okay, next thing. Error in clock placement. Very easy to come up with this formula for if you misplace the clocks, this is what you have. That's an algebra little assignment. But here's what it means to us. If the mile per hour clocked at 330 miles per hour, let's say that you had mismeasured the trough by 1/8 of an inch. Okay? The error would still be 0.05 miles per hour. And you can measure 1/8 of an inch with the tape. You can certainly do 1/4 of an inch, 1/8 of an inch. So basically, clock placement error, like truncation error, is negligible. Don't worry about it. Okay? Now the third type of error, the resolution of the clocks. The clocks have a 1,000th accuracy. And there's basically, so we have a clock here and a clock there, so there's 2 clocks. So we have essentially 2,000ths to deal with. Here's another formula you can work out. We won't need it. And it says that basically, if you give me the miles per hour clocked, then I have an upper bound and a lower bound for the actual miles per hour. So I have an upper bound and a lower bound in terms of what the actual miles per hour could be in terms of the clock based on this resolution of the clocks. So, for example, if 300 miles per hour was clocked, all you know is that that car went between 296.05 and 304. You don't know where, but it's somewhere in there. You can say that. So this is a very significant error. This is up to 4 miles per hour. So the other ones were not. To have a 1 mile per hour accuracy at 300 miles per hour, the clocks would have to have a resolution of 5 10,000ths, and they don't. Okay, so we found the error. The error was not because of truncation, and it was not because of clock placement. It's because of resolution of the clocks. Now, who first went 300? Kenny Bernstein is said to have done it, but according to our records, maybe it was Gary Ormsby in 1990, because he just kissed the 300. So really the probability is 0 that he did it. Okay, how about Bernstein in 92? Well, he might have a little bit. Mike Dunn might have done it. Bernstein at 301.7 in 1992. Maybe he didn't go 300. See? Maybe he went 297.71, and he didn't really. But we do know Scott Kalita out of Ypsilanti, Michigan, actually for sure did it. So we can say we safely, Scott went 300. Okay? But Kenny gets the credit. Okay? Let's explain why a quicker car will beat a faster car. Now you all remember, quicker means good elapsed time, faster means high top time. This is critical. So let's do this. So there's a bunch of words, okay? Bunch of words, but let's do it. Throughout the history of drag racing, there's been existed an infatuation with and a mystique about top time, but not elapsed time. Indeed, in the early days of drag racing, around 1950, there was only top time. People didn't even measure the elapsed time in the early days of drag racing. So, in part, this infatuation mystique comes from the fact that top speed is easier to understand and appreciate. We know when it says, you went 300 miles per hour. You have a feel for that. If I said you went 4.48 seconds, you say, I don't know what that means. I don't have any appreciation for that. So what? So, I believe that this appreciation was strongly nurtured and promoted by America's pre-drag racing involvement and successes in the quest for land speed records on the legendary Great Salt Lake courses at Bonneville, Utah, and other dry lakes like El Mirage, California. Okay? So we as a nation like to talk about top speed. And there's the blue flame, which has the land speed record at 622 miles an hour. It started in 1970. Gary Gabelich driving. I knew Gary Gabelich quite well in our drag racing days. And so this is Bonneville, and this is what we are used to doing. On the other hand, there was a lot of confusion as to why you'd have two cars racing, and we had no elapsed time. And the one car would say 150, this would say 130, but the 130 mile per hour car won. So, how can a slower car beat a faster car? As far as winning goes, the harsh reality is that as far as winning goes, all right, we don't need this, but look, as far as winning goes, top speed is meaningless. It is basically, elapsed time tells all. Moreover, it is initial acceleration that promotes good elapsed time. So let's go back to our hero, my brother Bobby, and the Green Monster, okay? Now look, remember Bobby slayed the Green Monster in 1959, and he still gets credit for that, and it's often, I saw it as recently as a year ago, somebody writing about Bobby and the Green Monster, okay? So let's see, why is that Bobby beat the Green Monster? Actually, the Green Monster was running about 174, and we were running about 148. But we beat the Green Monster, okay? So here's some basics on elapsed time versus top speed. We're going back to our formulas. Basically, distance is a function of time, velocity, acceleration. Now let's look at this. There's some mathematics, but notice I'm going to try to make it as painless as possible. Here's the acceleration for Bobby, and first is the Green Monster. See, Bobby jumps out with high acceleration and comes down. The Green Monster, slow acceleration, but gets strong. Now notice, final velocity is just the area under the curve. So the area under this curve and this curve is the same. So the velocity at the end is going to be the same for the two. The velocity at the end. So velocity is not a telling feature. It's area under here and area under here. What you want to see is what's the area for small time here, and Bobby is over here. The telling thing is distance. So area under the velocity curve, Bobby blows it away. Look at all the area under the velocity curve, especially here. So that's distance. So while the Green Monster is here, Bobby's here. And so the area under the velocity curve is the telling thing. So even though the two could have the same velocity at the end of the race, we have that the area under not the area under this curve, but the area under this curve, which is how far did you go in a fixed time, is extremely important to have strong initial velocity. So, simulation. I just ran two little formulas, and this is basically 1 minus t, this is t. And notice that basically the maximum acceleration is the same, it's here and here. And then you look at the velocity, and you see here's a jet car, and here's Bobby. And notice that at the end, the velocity at 1 is both a half, so they're the same. But look at the distance in here. Bobby has gone twice as far as the jet car, okay? So because the acceleration at the start is so high, Bobby goes twice as far. So if you're going to have acceleration, it's got to be at the start. So here's the fundamental theorem of drag racing. Okay? And I'm very proud of this theorem, and I worked very hard on it. Okay, so let me share it with you. So let's let S of t denote the time, distance, trajectory of a dragster run. Now, assume that the acceleration, S double prime, is positive in the time interval. That's standard. Suppose that you come up and you give a positive small duration pulse input. It's added to the acceleration at a specific time. So maybe you're going to kick the car, you're going to hit it with a hammer, you're going to have an explosive, you're going to have a rocket. So at one time along the strip, a pulse input is added to the acceleration. So the question, where should the pulse input be placed in order to minimize the quarter mile elapsed time, to make it the best elapsed time? Where should it be in order to maximize the top speed? So those are the questions that we ask. And this will tell us where you put your emphasis, wherever that pulse comes up. So let's take a look. Without loss of generality, the pulse input will be the indicator function of the interval list. That just means it's a box. And we're going to use hats on our things to denote new quantities. So this is interesting that here's the pulse input to the acceleration. Now the area under this is the pulse input to the velocity. And the area under this is the pulse input to the distance. So we look at these things, and we can actually write formulas that the new velocity after the pulse input is the old velocity increased by the constant delta t. So it doesn't change. It doesn't matter where you added that pulse. See? It just is going to increase by delta t. On the other hand, the new distance is going to be the old distance plus t minus this. And this is just the formula for the area, or this curve right here. And so basically this tells us that since we're subtracting off t naught, you have to make t naught as small as possible. But this tells you the same thing here. If you want to make this as large as possible, slide this curve over here and start it right there at t naught equal to 0. So our observation is velocity doesn't depend on where we hit the pulse, but distance increases as t naught decreases. So our conjecture is for best elapsed time, place the pulse input as early as possible, i.e. at the start of the race. Now, and we also say no matter where you place the pulse input at each time, the velocity will not change. I mean, it's going to be increased by a constant anywhere you want. So put the pulse input wherever you want. Okay? Now, we're wrong. Okay? We're right about elapsed time, that it's uniquely minimized by placing the pulse input as early as possible, i.e. at time 0. Okay? The top speed is uniquely maximized by placing the pulse as late as possible. And I want to show you how we went wrong. So if we solve for elapsed time, it's 1,320 feet, we see various mathematical notions about decreases and increases of stuff. So basically we see that the elapsed time decreases or increases with where we put the pulse beat. So if you want this to decrease, we put this equal to 0. So t equals 0 uniquely minimizes the elapsed time. On the other hand, the velocity, while it's true that it looks like this, what you have to observe is that since this is monotone increasing, the derivative is monotone increasing, the velocity is because the acceleration was positive, that basically the longer you make the elapsed time, the more velocity you'll have. So so in other words, since this is monotone increasing, that the velocity at the final time will be uniquely maximized when t hat final, i.e. the elapsed time, is maximized, i.e. when it's as large as possible. So in other words, what you want to do is make this as, so this is small as possible, but for top time you want to make the elapsed time as big as possible. Okay? So what does that say? Our fundamental theorem takes a big step towards explaining why fast cars are often not quick and quick cars are often not fast. The two work against each other. In our model, slowest elapsed time gave fastest top speed. Okay? The slowest elapsed time. Bless you. In our model, so in other words, if you want to get good top time, make sure that you have a slow elapsed time. If you want to get good elapsed time, don't worry about the top time, just start off at the front. So here's the translation to another form of racing. If you want to win a short foot race, then don't sprint or accelerate or kick at the end. Accelerate as much as you can at the start and be totally undone at the end of the race. And this is how Ben Johnson beat Carl Lewis. Okay? He went bang! And Carl Lewis was coming on and coming on and coming on, but the race was over. Okay, so car with good initial acceleration will win the race. For dragsters, acceleration is large and then drops off quickly. This explains why dragsters do such a better job on elapsed time than they do on top speed. Webster won drag race, a speed contest between automobiles. He missed the essence of drag racing. Speed should be replaced with acceleration. This has been done in Webster too. Okay, so let's go into something. So we took care of that. Now we know why cars with better elapsed time are going to win. And if you didn't do anything, you should try to do that. So let's quickly go into what is the maximum acceleration today's world-class dragsters achieve in a quarter mile. In the early days of drag racing, there was an implied belief that one g-force, the acceleration of gravity, was the fastest that a car could accelerate. And I'm going to show you. In a freshman physics book that's used a lot in many courses, here's an instance of the implied belief. You want to make a car go really fast, push it off a cliff, and it'll be accelerating 1g. Okay? But I want to say that's wrong. Okay? So it goes from 0 to 60 in a little under 3 seconds. Actually, it's 2.74 seconds. Okay? Now here's the reality gap. That Larry Dixon went 4.48 seconds to 330. 1g is 9.06, 198. It is unbelievable that in 1 second, a world-class dragster like Larry Dixon is going 100 miles an hour. Okay? And I recently, we'll speed up, but I have to tell you this story. I recently got an email from somebody who said, My stupid friend says that a dragster can go 100 miles in 1 second. And this is stupid, it's ridiculous, and we have a lot of money betting on this bet. Would you please straighten it up, okay? And so I sent back and I said, your friend's right. And he never answered me. Okay, so here's the 1G. So basically, Art Christman went 940 in February 7th, 1953. Barney Navarro, in an article in Rods and Customs, said, the fastest a car can go is 167, so going 140 is really quite good. Now, in the same article, in August, Navarro said, a lot of readers have asked me, what's this formula? And others have challenged. So Vosburgh was kind enough. Now, Vosburgh was an aerospace engineer in the aerospace industry in California in the 50s, but this is 1953. So here's Vosburgh's derivation of 1G limit. Newton's second law of motion, F equals ma. You solve for acceleration. Then you look at force over weight. Now, there's a notion in physics called the coefficient of friction, which basically tells you that the force that you can assert to the pavement is never greater than the weight of the car. So force over weight is less than 1. And if you put that less than 1, then the acceleration maximum is less than 1g. And that was Navarro's stuff. And then he put in some formulas, and it says 167 miles per hour is the best you can do. And Navarro, to prove his point, said, we took Mr. Vosburgh's letter to several engineers who immediately whopped out their slide rule, and after a few minutes came to the unanimous conclusion that the formula is indeed correct. Okay? So the formula is okay, but what about the assumptions? Now, in 1954, Don Yates and Vern Mickelson went 144 in 8.99 seconds. Now notice that that's better than 1G. Now this is at the time when this controversy was raging. So the drag racing community, theoreticians, racers don't care at all, okay? The clocks gave a bogus time. You can't beat 1G. Now it's interesting that the Yates and Mickelson time was not entered into the record books, and we did not see another sub 9-second elapsed time for 3 years, okay? This is the car, $5 to anybody can tell me what kind of engine. Driving the last nail. So much controversy that finally the National Hot Rod Association decided to get together with Klondike and go to the Pomona drag strip, take 3 cars, set clocks at a tenth of the quarter mile, 10 clocks, and see if indeed it could happen. Now the Nichols brothers Quincy Auto Parts dragster covered the first 132 feet in 2.066 seconds, okay? So Barney Navarro writes in June of 57, using distance equals 1/2 AT squared, that would be what would be required if it was average. So he's giving us essentially that the time of 2.066 translates into 1.92 Gs for average acceleration. And so it's got to be better than that. So the net effect is that as of June 1957, the myth of maximum acceleration of 1G was effectively laid to rest. Okay? So we want to see what's the fastest, the maximum acceleration. So we're going to do the same thing. We're going to take our data and we're going to run it through the, we're going to do some interpolation procedures, a polynomial, and see what we get. So we do the same thing. We have the data, we have our formulas, we have our stuff, and we do interpolation. Now notice this. This is the, all the data points put together. That's a polynomial at degree 7 interpolating our 8 points. That's a beautiful polynomial at degree 7. See, everybody thinks polynomials are supposed to go like this, okay? But that's beautiful, okay? And so if we take all these things, we find out that with a polynomial of degree 2, we have that Larry Dixon did 5.07. If we do 3, we get this. So all the way up to that polynomial that you just saw, this beautiful polynomial right here, if you take the second derivative max there, you'll see that it's 7 Gs. So according to that polynomial, it's 7 Gs. Now the estimate of 5.07 is a guaranteed lower bound, because if you put this formula in, it tells you that, look, for a parabola, this is the average acceleration you have to do to accomplish the task. So in all cases, the maximum acceleration occurred at time t equals 0. Remember our findings in the study of quick versus fast. It should not be surprising that we have seen that the perfect elapsed time machine must have extremely large acceleration for small values of time. Okay? It's hard to believe that if the acceleration is 7 Gs, and then we solve for mu, we basically see that the maximum force asserted to the ground from the wheels has to be 7 times the weight of the car. Can it be that the downward force exerted by the tires on the asphalt is 7 times the weight of the car? And the answer is yes. Look at that. Okay? It's squashing the tires. So what's wrong? Do you believe that Newton's second law of motion is wrong? Or do you believe that the coefficient of friction theory is wrong? So let's go back to first principles. And let's look at mu defined as maximum force over the weight. Category 1 of factors contributing to mu. Traction enhancement factors, non-smooth irregular asphalt, soft spongy wide tires, low tire pressure increasing the contact surface, the burnout, hot, gooey, sticky tires. These 4 factors create a tire asphalt gear drive effect that increases the value of mu. So it looks like this. It's a gear running on a gear because the asphalt is coming through here, and so this gets an arbitrary large mu. Another one, these are very interesting factors. Weight force enhancement, the aerodynamics of the wing, the rotation translation factors that come from mechanics, the lifting of the front end, that asserts more weight down. So it forces effectively the weight of the car increases, and so for a given traction environment, the utilization of more engine force can come in, and it increases mu. So we have 2 ways to increase mu. Now, a good research issue, which we've been talking about with some graduate students, is how significant is each one of these enhancement factors. Okay? Unfortunately, the net effect of the Vosper-Lengy controversy was to cause the drag racing community to have no faith in mathematics or physics. Okay? Maybe that's the way it should be. Okay? This is the last study. Okay? So we're going to go through real quick. What is the dragster's acceleration profile? Remember, does it look like this, or what does it look like? Okay? So this is our last study. Now, in the early days of drag racing, it was believed that, and probably true, that the dragster's best rate of acceleration right here was not at the start of the race. You rolled off, you went fast, and you came down. After all, this is certainly the case for your everyday go-to-hell automobile that you drive in the street. Okay? Boom, boom, boom. Okay? So why not? Now, Barney Navarro in 1957 said, that's not true. In our experiment at Pomona, every car started out accelerating best, and by taking average time, he said it got worse. So this is what Navarro saw. He said, contrary to popular belief, the acceleration for a dragster is decreasing in time. It starts large and gets smaller. And here's his proof. Here's his proof. Look at this. Average velocity. The gap between here and here is larger than here to here and here to here. Therefore, the acceleration is monotone decreasing. Okay? Proof. And for an editor of a magazine, that's not a bad proof. Okay? It's not a bad proof. Now, here's our observation. Dragsters are unbelievably better at elapsed time than they are at top speed. So let's study this acceleration profile and see what we get. So basically, current belief is that it looks like that. Everybody believes like that. I mean, the editor proved it. Okay? Now, we're going to fit our data back into the curve. And our first pass said, here's the beautiful polynomial, here's the beautiful velocity, and here's the acceleration. It's got a bump. Okay? So that's not what it's supposed to do. We're going against what everybody believes. Okay? So there's a blip here. The acceleration is not monotone. It's supposed to come down like this. All right. So polynomials are notoriously bad. So let's do a conservative C2 cubic spline. Same blip. Let's do something even better. We build a super interpolator. Same blip. The blip is there. So what do? We go to the experts, including Carl DeBoer at Wisconsin. And the experts say, Richard, the blip's not supposed to be there. You've got bad data, or it's an artifact of the interpolation. And so we keep trying, and we try different data, and the blip won't go away. So after considerable time, we say, experts, you're wrong. We're going to show you. And remember these traction-enhancing properties and these weight-enhancing properties. Here's what we're going to do. We're going to look at the force that comes from the ordinary. This is the ordinary force, and this is the extraordinary force. So this comes from everything that would be present if we didn't have these enhancement factors. That means the soft, gooey tires, the transfer of the front end lifting up. All those factors I listed are going to come in the force that comes here, and the ordinary ones will come here. Okay? If we do that, then we have acceleration is going to be 2 components. It's going to be ordinary plus extraordinary. Coefficient of friction is ordinary plus extraordinary. And we don't mind if the ordinary friction is less than or equal to 1g. We'll give that to Vosburg. Okay? But here's a blip explained, is that if the ordinary acceleration looks like this, and the extraordinary acceleration comes on really strong at the start, like this, and then it goes away. So this is the hot, gooey tires which get cold, spinning the wheels, which eventually you stop. Everything here if you add that curve to that curve, you get that curve. Okay? So basically, one possible explanation is that the blip comes from adding a curve that is the ordinary acceleration plus the extraordinary acceleration, and there's the blip. Okay? So in terms of Larry Dixon's run, this is the acceleration curve. This is the extraordinary acceleration. This is the ordinary acceleration. You get them together, and you get that. So we're very proud of ourselves, and we think that we really has explained something. So we ask this question. If FT has a blip at exactly the same, and according to this formula, so if the acceleration blips, then the force blips. So FT has a blip at exactly the same point. So what would cause a decrease in effective force even when the engine is still running really good? Okay? Well, excessive wheel spinning has to be it. Okay? So the excessive wheel spinning will drive the force to zero, the acceleration to zero, and everything to zero. So our conjecture is that the blip signifies a time point where the wheels stop spinning excessively and traction is restored. Okay? And you saw those cars, they spin their wheels excessively. So it's to maintain that. So do all the drag racing cars have blips? Yes, if they can spin their wheels excessively. Bottom line is you must spin to win. You have to spin your wheels. If you don't spin the wheels and you come off, you're going to have ordinary acceleration. So you have to have extraordinary. Now, was our friend Barney Navarro correct? Did the Quincy Auto Parts car not have a blip? Did cars not spin their wheels enough in 1957? Was Navarro's tool too crude to pick up the blip? Let's see. So here is the 10 pieces of data, and we put a polynomial through there. It's going to be a 11th degree polynomial. It looks pretty nice. Uh-oh, the velocity is starting to come in like this. What about that? There's the blip in the Quincy Auto Parts car that Barney Navarro said, with his proof, had to have monotone acceleration. So there's the blip. But Navarro couldn't see it. His method was too crude. He couldn't know how to measure second derivatives. He just took this and this and this. So the blip lives, and it's been there for many years. This is 50 years. I mean, nearly 50 years ago there were blips. All cars have blips, okay? Now, all right, so basically we're going to go through real quick here, and we're going to go right back to here, and we're going to say, so okay, now where do we go, okay? And of course, for cars it's easy. We're going to go quicker and faster, of course, okay? But where do we go? I gave this talk at Rice University, and there were a lot of people in the audience. It was a wonderful audience. Not as wonderful as this one, but it was a wonderful audience, okay? And there were world-class mechanical engineers who knew all about mechanics, and there were physicists and everybody. But more important, there was a person who represented people from California and the Discovery Channel. And they said, we want to do something for the Discovery Channel. So we had people come out, directors and producers from the Discovery Channel, from people in California. And so they want to put some money into trying to make this as a video, either for children, i.e. we have to tone it down in the sense of math, or for the community, or something for maybe TV or something. We don't know. But all of a sudden, a lot of people are asking a lot of questions. And all I wanted to do was just explain a couple little things that have been puzzling me for a long time. I didn't expect the blip. I didn't expect the blip. The blip came out of the experimentation. And notice, world-class people said, it's not there. It's not there. And I went back with a postdoc, and he said, Richard, we can't get rid of it. Okay? It's there. So there's some understanding. And you could use some of this understanding to maybe make better tires, make better cars. We already have several ideas on how to improve this thing. But we don't know where we're going. But I do know that I wanted to share this with you. And I do thank you for being such a good audience. Thank you. Sure. I mean, I love questions that say, you're wrong. Yeah.
Firestone or Pirellis?
What? I mean, no, those things are probably Goodyears, okay? Goodyear, see, land speed records and drag racing strip records, the tire was the component that needed to be improved. And so we used to stand around and do things until Firestone became committed. to making good tires. That's when Gary Gablick set that record, because tires would come apart at 300 miles an hour. So as soon as technology in tire making came in, it was a pulse input, just immediately. And Firestone led the, Goodyear led the way on that. Pirelli does, Formula Ones and go-cars, circle cars. Drag racing is a serious sport. Goodyear did get into it, and they do it. Okay? Other questions?
How about aerodynamics? Can you compute optimal form or something?
Well, this is a good question. Now, I argue this. The same question was asked at Rice by a very, very competent mechanical engineer. And I said that the aerodynamics are not critical at the start, okay, t equals 0. They will come in down the line, okay? But they're not critical, and I argue that aerodynamics are not a factor in acceleration in time equals 0 to epsilon. That's not going to be a factor. But I have been convinced, and I didn't believe it, that weight transfer, okay? There's a couple engineers telling me weight transfer, in other words, as it tries to pick up the front end, effectively is pushing force down on the rear wheels, that is a significant factor, and I have one graduate student saying that it's as much as 20%. We'll follow that. But I maintain, we can sometimes study that, but the aerodynamics, I maintain, is not a factor at the start. It's a significant factor because the force from the wing is at least 5,000 pounds at the end of the race. But I don't think it matters at the end. Back there.
How about the recoil tire, the effect of the slingshot when the drum, the wheel drum at first acceleration rotates faster than the outer rim of the tire.
Well,
Tires are soft and the walls can wrinkle. You get a rotational differential between the inside drum and the outer tire.
yeah.
Part of the sucking down that tire.
There's no doubt about it, except today's dragsters, they put screws into the wheel and the tire, and they don't let it slip anyway, okay?
Well, there's no slip. It's actually the rubber of the tire is
That can be a factor. That can be a factor. I will give you that. I will give you that can be a factor. See, after giving this talk enough times, there's a lot of factors that, But notice that I'm not, I'm not in mechanics, so I don't have to, but so notice what I did. I did a mathematical approach. I said, here's the ordinary, and everything else is extraordinary, okay? So,
study that in the extraordinary forces.
yeah, well, we're going to add it in there. Maybe next time I'll put that in there, okay? It's a good point. And that's why I said as a research issue, we have to see, are they important? I would always, in the first days, I would blow people off and say, that's not important. But a bunch of engineers attacked me one day, and I said, okay. I said, but I'll put yours. That's a very good point, okay? Now, I'll tell you this. In the old days, about 1965, a fellow named Pete Robinson out of Oklahoma built a car. It was a Chevy. And he jacked up the rear end, and he got the wheels going real fast. And when the light said go, he just pushed a button and the jacks came down. And he blew everybody away, okay? Because the wheels were spinning and that force came forward. NHRA said, it's too good. They didn't say it's too good. They said it's too dangerous. It's illegal, okay? Out. It was too good. And Gartless had said, wow, that's going to be the future. I'm going to do that. He's going to do it. So he just blew everybody away with a little Chevy. But NHRA said, no, it's too dangerous. He said, no, they work like gyroscopes. It's safer. And, NHRA said, it's against the law. Okay? It takes the sport out. Okay? Other question? Yeah.
I got a question.
Okay.
A friend of mine's Don Ness, a postdoc car.
Yep.
He was doing a bunch of research on Tapia. He's a wind tunnel. So with my airplane, if I wax my airplane, wash it, I get 5 miles an hour faster in airspeed.
Hold up.
I said to him, in the wind tunnel now with the friction coefficient, wouldn't that affect that by having a smoother body? He told me, no.
It will make a difference, but here's what happens with dragsters. See, these dragsters have 5,000 horsepower, okay? And so basically they're over horsepowered. And so it would make a difference if we were at the point where we needed to worry about additional horsepower to make the car go faster. But it will make a difference. People know that if you polish the car and make it nice, it'll make a difference. In fact, on slower cars, people do that. But with the dragsters being over horsepowered, that he's saying to you, that's not going to be such a significant issue. But of course, this goes back to your point. I would argue with him that it will make a little difference, but he's going to say it's not making a significant difference because I have so much horsepower. See, the problem here is not to make more horsepower, it's how do you get the horsepower to the rear wheels. This 5,000 horsepower just goes bam, okay, and it's there. So the answer is, it's not going to be significant, like the aerodynamics is probably not going to be significant, like your wheel spinning might be significant, but it'll be there. It will be there. You had a question?
Yes, this is a little bit different, taking your topic and turning it on its head about deceleration. Cars are coming with anti-skidding devices now and like that. What does your intuition tell you about the quickest way to stop? Slamming on and locking up the wheels?
That's an excellent question. Okay, that's an excellent question. Okay, now you all live in ice country. Okay, I live in Houston, Texas. Okay, okay. So we had ice in Houston about 6 years ago, and I am not exaggerating, but in a period of 4 hours we had 1,100 accidents. Okay, okay. So you notice that these cars all stop with parachutes. Okay, and we're not going to put parachutes on cars in the street. Okay, okay. But that's important. But I think absolutely, my own opinion is, no, you don't slide the wheels. You don't slide the wheels. For the same reason that you don't slide them in ice. I lived in Madison for 2 years. Okay, you slide them, you lose it. If you can do these ABS brakes, you just start it off and on and slow it down right where you're going to lose it. That's a winner. That's a winner. Okay, there's a lot of technology that can be used on how to stop cars safely that we can learn from here. It's an excellent point. No, you don't slide the wheels. You lose control. Okay? We used to live on a hill in Madison, and when it iced over, my wife would put on the coffee pot and say, look, everybody's going to slide down the hill and hit each other, open up the doors and put on the coffee. Okay, anybody else? Sure. Okay, let's go over there and let's come back here. Okay.
Do you know if the blip exists on the same way for a door slam or a full body car?
Yeah, that's, I mean, yeah, see, here's what I say, okay? And I said, if the car spins the wheels, see, you have to spin your wheels. In fact, I skipped a lot of stuff, and there's some statements from people who, in the early days, would say, spinning the wheels. In fact, Charles Manning had some great statements in 1953, the legendary Manning sports car. And he said that if you spin your wheels, then you're going to get this acceleration above, 1.2. So here's what I say as a mathematician. If the ordinary acceleration is like this, and, you're going to have to get a good amount of acceleration at the start to get the blip. Now, blip may be small. So I say that any car that has good traction spinning the wheels, yes, the blip will be there. It may be small, but it'll be there. Okay? It's a car that rolls off the line where it won't have a blip. Okay?
Getting back to your aerodynamics.
Yeah.
One of the reasons it doesn't affect the car as much is because a drag race car spends much more time at the low end of the first half of the track than it does at the top end, where your speed will affect.
That's correct. Yeah. That's correct. But notice that wings used to be that they didn't make much difference at first, but it's getting closer and closer. But your point is well taken. Somebody back there wanted to say something. Somebody back there, I know, left.
Why do they make them so long nowadays, these cars?
But that's what I was told by an engineer. That, okay, and if it's short and the power transfer lifts up the wheel, then you lose, okay? And so if you make it real long, the force that you're trying to use doesn't pick up the front end, but effectively that same force goes into pushing the tire down. That's what engineers told me, okay? So, sure, anybody, okay, you. Yeah.
What on Nixon's world record run, he almost went over.
And I have shots and shots of people going over, yeah, but you go ahead.
So I mean, you have to, is that what you have to do to break the world record, is almost bring it back over itself?
Well, that's what my engineering consultants, mechanics at Rice tell me. Yes, that's a significant factor. See, the first time I gave this talk, I just had this tire enhancement stuff. And I was jumped on by engineers saying, of this transfer is critical. So if we get some money from these people, we will do some studies on that and see what it is. They say yes. They say yes. And I say, you know more about it than I do. I don't know. But that's exactly what they say. Is one of the things that I didn't show, and I have a slide in there, when my brother set the world record, he came back and he told me, Richard, the front end was just lifting right and the tires were hazing just right. So he said, wheel spin was perfect and front end lift was perfect. And he didn't even know what he run. And he looked at me and he said, that was a great run, wasn't it? I said, it was a world record, Bobby, on those two issues. He knew it. He knew it from those 2 points.
But you can't control that. You can.
Watch people riding motorcycles jump. They can totally control the elevation of their front tire while they're in the air.
Yeah. You have to, I mean, his point's well taken. But you have to go into that area and see how can we control it in the most effective manner possible. Dragsters do that. They say it's getting in and out of it or feathering the clutch. They say the front end was coming up, so I got off of it. And motorcycles in particular do that extremely well, okay? So you have to say, let's make it easy for people to do that. In 1992, Gary Ormsby put in an analog computer to monitor the wheel spinning so the front end wouldn't go up too much. It was very successful, and NHRA outlawed it, okay? Go ahead.
Is it smarter, or can you engage the blip sooner, and then would it be wise to engage, lose, and re-engage the blip? And that bit about the front end coming up, do you want to lengthen the front end or add a little more weight?
Yeah.
Got a little more inertial load that's going to go back to the tire, that's going to help you?
All those things are excellent questions that need research issues, okay? All those. In fact, there's people from California wanted to say, we're going to form this study and find out what we should be doing. They're all excellent questions. I don't know the answer, but of course you can do something, okay? Yeah.
If the force to friction is based on the weight on the tire and
Yes.
the coefficient of friction between the tire and the pavement, how does a wider tire help?
Because, see, the coefficient of friction is 1 point. So what I gave Vosberg was that this is not your standard coefficient of friction situation. So what I did as a mathematician, I said, look, the wider tire, the softer tire, because see, the theory of the coefficient of friction says that it really doesn't matter and the contact surface is going to be a point. So what I said, all that stuff what you're talking about, I'm going to call the extraordinary coefficient of friction. So it all goes there. Everything that you all have said goes in my wastebasket called extraordinary coefficient. But that's a good point. But see, that's where Vosberg made the mistake. See? He said, and I had some quotes, but I had to go fast. There's some people, very knowledgeable people, in 1953 who told Vosberg that, and in fact, Charles Barney, no, in today's world already we're doing 1.1. Okay? So basically that model was very simple, and he got into trouble with it. Okay? And you know, they wouldn't think of asking a PhD to do this. I mean, they just asked some editor or somebody, and everybody said, look. And so that's what made mathematics and physics look bad. If they had asked any reputable PhD, they would have said, oh, you can't model it. Mathematician would have said it can't be done. Okay? Yeah.
Could you say something about how drivers might have changed the materials for tires in response to changes in the surface?
Yeah, I mean, that's an excellent point, okay? That's an excellent point. And people do. You go to a track and you say if it's a really cold surface or if it has really good bite, or basically maybe somebody exploded and there's oil on the strip. So the way you don't change the tires. On a dragster, they have a clutch, and you set the clutch. The driver doesn't set the clutch. So you say, look, it's a particularly slippery track, okay? So then I'm going to back off on the clutch so the wheels and don't grab as hard. And so you watch other cars, and you run, and you say, look, Houston, Texas, today, the traction is excellent. Tomorrow, maybe it got oil on the thing. And so you try to guess. And that's why the pit crew chief is the highest paid, because the pit crew chief has to guess these things. And I want to add to you that when my son used to race BMX bikes, which we did a lot, I was incredibly good at guessing track conditions before anybody else could, and he would win on new tracks, okay? Not because he was that faster, because I could guess the conditions better, okay? And that's what a crew pit driver will do, okay? Exactly that. And that's why the records are set in Houston, because it's, low elevation and there's a lot of green grass around it, so basically they get more oxygen. Okay? Good question, very good question. Anybody else? Sure. Okay, let's go two. Okay, go ahead.
Since spinning tires is the fastest way to run the corner, but isn't static friction higher than dynamic friction?
Those are all good questions. Excellent questions, okay? I've had people ask that question about going around a corner and stuff. And I don't know. See, I don't know. The only thing I'll add on going around corners and stuff is that A.J. Foyt out of Houston, Texas, had the reputation of being able to read a corner better than anybody. And he could go into it right where it was going to lose control, and he used to win races because he could call a corner better. So he had some incredible ability to read when he was going to lose the car and stuff like that. That's an important question, a very important question. I don't know the answer. Okay? Over there.
Have you reviewed the effect of one effect flywheel configuration?
I'm sure people have thought a lot about it, okay? And in the old days, there used to be a lot of conjecture. Yeah, but I don't know anything about that, really, okay? Your question.
Has anybody ever fit a car with accelerometers and mapped the blip
no. See, no. See, you're all a very educated and a very good audience, but you understand that, look, before I started asking these questions, nobody was asking any questions about things like this, okay? I mean, it was just, you know, physicists and mathematicians don't know anything, and, you know, but as a hobby, I started asking these questions. And that's when, in Houston, Texas, when I had these people in the audience, they said, we want to answer some of these questions, and we're going to get you dollars to do it, okay? But you're asking very good questions that, here's what I say to you. We've gone so far from what people used to understand, okay, that now, and I'm afraid a little bit that if we start to get too technical, it won't be a hobby anymore and I won't enjoy it anymore, okay? But it's going to be research and we'll have to compete with other people. And I don't want to do that. Okay? Anybody else? This is therapy. And you're all adding to my therapy, okay? I don't want to see, you know, referees' reports on this, okay?
Okay, well, thank you very much.